Alright, here we go. CCNA1, Chapter 3, Network Protocols and Communications. It's an exciting one. So I'm going to start off with showing you how to statically set again, because I just want to make sure you guys know how to get into those settings to set DHCP or take DHCP off. And so we do a right click, open network and sharing. That brings up this right here. We say change adapter settings, which brings up this right here, and then we say properties. Okay, so in properties we then look for IP version 4, which we're going to set. If we want to put it static, we say use the following. If you guys want to use Google as a DNS, it's always a safe bet. It's just 8.8.8. Otherwise, we'll talk about IP addressing in the future. Okay, so now we're back to this. In this chapter 3, we're going to explain why protocols are necessary in communication, explain the purpose of adhering to a protocol suite, explain the role of standards organizations in establishing protocols for network interoperability, explain how the TCP/IP model and the OSI model are used to facilitate standardization in the communication process, explain why RFCs became the process for establishing standards, describe the RFC process, explain how data encapsulation allows data to be transported across the network, explain how hosts access local resources on a network, and explain how local hosts access remote resources on a network. Exciting stuff this time. Alright, so we're skipping that. What is communication? Well, it's someone talking to someone and coming back. And so, what do we have in human communication? Here we go. We have a message source, then we have a signal, the transmitter, transmission medium, a receiver, and then the destination message. Well, that's the same as what we have in computers, right? Same thing is happening. Source message, signal across the medium. So it starts signaling. That'd be like me talking, and I talk to you, hear it through sound waves. In a computer, we hear it through, well, with this wire, we hear it through electrical signal. Then it receives it just as your ears would, and it gets the destination message. That's the exact same thing. Computers talk in a similar fashion as we do, just using a different transmission and medium. So what's important to communication is establishing rules. Otherwise, maybe you look at this message right here. This is pretty entertaining. They stop using spaces and that kind of thing, and it makes it very hard to read. So we translate it, right? So we need rules so that we talk fast enough, or we don't want to talk too fast. We don't want to talk too slow. Sometimes I talk too fast, so hopefully I'm not doing that for you guys. And so people can understand it, and we have timing between it. You know, we can't have two people start talking at the same time. So what do they say? What are the rules? We want to identify a sender and a receiver, common language and grammar, speed and timing of delivery, confirmation or acknowledgement of requirements. All right, so that's the rules we need. And protocol is just a suite of rules. That's what protocol means, is a rule. This is how it's going to be done. Alright, so we go into message encoding. Alright, and so let's see what they say about message encoding. We're conveying I don't know, what is that? A sunset. And so this guy understands the sunset. Now, what was the encoding? This is going on to computers. And so what it's doing is encoding, let's say, ones and zeros into a packet to transmit across there, or across multiple medias. And we will talk about that more in a bit. But so it's encoding ones and zeros to transmit across the wire, to then be received as ones and zeros, de-encoded, and we understand the message. That's what this is trying to portray. We have to format the message. As I've talked about before, IP is networking is a lot like the mail system, right? We're sending packets. We're not sending packages, but we're sending packets. And so we come from a source address to a destination, and we both have addresses so that if they fail to send, they can come back, and they can also get there, right? Yeah. We need rules on message size. If it's too big, it gets confusing, right? So we have to set a certain size. Just as this poor guy got confused about the sunset instead of that way. So let's see how computers do it. If we don't set, it's called a window size. If we don't set this window size, if they don't understand what they're transmitting in, the encoding doesn't work correctly. Then we have to time it correctly, right? Which is, I'm talking about how fast it's going to go. They're talking about access methods, I guess, on this timing, but it basically is just saying the access method that says we can't both say it at the same time. All right, so that's part of the timing, and then we have flow control. And flow control is, you don't want to send too fast. That's the talking too fast or too slow. You can't talk at the same time. You can't talk too fast or too slow. And then we have response timeout. So if I say something to you and you just look at me with a blank stare, after a while I'm going to say it again because I don't think the message actually got there. So those are some of our timing rules in there. And then we have delivery options. So we have unicast. That would be me talking to one person. Multicast, which is one to many. Alright, so we have many people. Or to everyone. That's a broadcast. So a broadcast goes out to an entire network. A multicast goes out to multiple hosts on a network. And a unicast goes from one to one. So those, we'll be talking about those more in the future. So now we're going to go to protocols, rules that govern communications. So protocol is a rule, right? So we're going to talk about routing protocols. We're going to talk about layer 2 protocols, layer 3 every kind of protocol. And so there's protocols that are rules at the physical layer, at the net. There's a 7-layer model we're going to be talking about shortly, and we have protocol suites for each one, which is just the rules that they run by. So the role of protocols, we'll just go with how the message is formatted or structured, the process by which networking devices share the information about pathways. Alright, so this is how it's formatted. This is the pathways. This is basically, this is just talking about there's rules for how and when the error systems and messages are passed between devices, the setup and termination of data. It's just, these are rules that we're going to learn about. The next chapters are going to build off of what we're talking about here, and there's a 7-layer model. We're going to talk about the TCP/IP model and the OSI model, and there's protocols for each of these models, and we're going to talk about the rules, and they do some of these things that we're seeing in these slides. Alright, so here's some protocols for the application layer. Alright, a protocol for the application layer would be HTTP, and this is web traffic, which it's actually now HTTPS, but your most basic form of web traffic is HTTP. Alright, so that accesses a web traffic, and that's a protocol that allows you to access the web. Then we have TCP, and that is a layer 4 protocol that allows for information to be sent, and it makes sure that the information got there. And so HTTP is actually a TCP, has a TCP port number. And so we went from the application layer to the transport layer, which is TCP. Then we have the network layer, and a protocol at the network layer is IP, Internet Protocol, which is the addressing. And then for the data layer, the encapsulation protocol is Ethernet if we're using our normal switches that we've been talking about. So here's protocol suites and industry standards. So this is basically everything runs off of TCP IP now, but in the past, actually ISO still runs some things, I believe, but I'm not sure. I think like some telephone standards are still ISO, but AppleTalk and Novell, before TCP/IP became a standard, that an industry standard that everyone would use, so that you didn't have to buy an Apple device. Like if your network was Apple, you had to use AppleTalk, and so everything had to be Apple, and it didn't work with, we'll say, IBM devices or Novell devices, right? So TCP/IP is a general is a standard for open standard for all industry on this model. And so at our application layer, we have HTTP, DNS, DHCP. ISO had these things. AppleTalk had AFP, and Novell had NDS, right? And so these are the different layers of what use. But what we really care about is the TCP, UDP, everything here. This is just showing you the different suites, but we're not going to worry about them, except for Ethernet, PPP, frame relay, ATM, and wireless LAN. These are all layer 2 encapsulations that we still use. But as for that, we just care about TCP/IP. I don't dwell too much on this other stuff. Alright, so here it just kind of goes through a history of all of the protocol suites. If you guys are interested, it's very interesting, so you guys feel free to look through it. Alright, so here's our TCP/IP model and how it communicates. Alright, so these different layers hand off to each other through different protocols. I believe you guys can click on all of these. We'll be studying these in depth. There's a chapter on each one of these layers. Okay, so feel free to look through some of this stuff, but the most important part is right here where we're making what we call encapsulation. And so this is the building of, this is what's sent through frames to devices when we do network communication. We have our data layer, data link layer, which has a header and a trailer, and so it encapsulates the IP information. So this has the most basic form in this IP is it has a source IP address and a destination. Then we have some TCP port numbers, which then tells it what application to use, and so then the application brings the data, and so this would access a web page if we were to watch it, and then it sends it back in reverse, but that's for another day in my opinion. Okay, now we have standards organizations. Alright, so as I said, there's these open standards, and we're going to hear all about them. So we have the Internet Society, the Internet Architecture Board, the Internet Engineering Task Force, the Institute of Electrical and Electronics Engineers, the International Organization for Standardization, and they all do something different, and that's what we're going to talk about. Probably the most important are the IEEE and the ISO are probably talked about the most in this content. And so, let's see. The Internet Society is responsible for promoting open development, evolution, and Internet use throughout the world. It facilitates the open development of standards and protocols for technical infrastructure of the Internet, including oversight of the Internet Architecture Board. Alright. The Internet Architecture Board is responsible for the overall management and development of Internet standards. The IAB provides oversight of the architecture for protocols and procedures used by the Internet. We're just going to call that good. The IETF's mission is to develop, update, and maintain Internet and TCP IP technologies. One of the key responsibilities of the IETF is to produce requests for comments, RFC documents, which are memorandum describing protocol, processes, and technologies for the Internet. We'll call that one good. The Internet Research Task Force is focused on long-term research related to Internet and TCP/IP protocols, applications, architecture, and technologies. While the IETF focuses on shorter-term issues of creating standards, the IRTF consists of research groups for long-term development and efforts. Sorry. Yeah, we'll call that one good. So now we get to the IEEE. And so you guys have heard of the IEEE before and you didn't even know it. So Ethernet 802.1, or no, 802.3 is Ethernet, so all this wired stuff. And then we have wireless 802.11. So you guys have probably heard 802.11n, 802 A, B, G, maybe AC, and the newest one's going to be AD. And so that's wireless, but they're doing all these standards. 802.16 is that broadband wireless that I was talking about, the WiMAX or the LTE. Okay, so let's see what else is important about them. I don't know. They develop these anything you see with an 802, you know it's an IEEE standard. The ISO. So the ISO built the OSI model, which is something we're going to study, and so that's what they also have many technologies for, I don't know, like telecommunications and that kind of thing. They have open standards for that. We'll look at them in the future. Okay, so feel free to look at these other organizations, but the one that is the most important is probably IANA, which is the Internet Assigned Numbers Authority, is a department of ICANN responsible for overseeing managing IP address allocation, domain names management, and protocol identifiers for ICANN. So all public IP addresses are registered through the IANA, alright, which is a part of ICANN, which is the Internet Corporation for Assigned Names and Numbers, is a non-profit organization based in the United States that coordinates IP addresses, allocations, the management of domain names used by DNS, and protocol identifiers or port numbers used by TCP and UDP. ICANN creates policies and has overall responsibility for these assignments. So basically they make the Internet work. That's what these do. Without these huge DNS registries and registered public IP addresses, there would be no public Internet. Alright, so we've been talking about these models, and so we see the OSI model here, we see the TCP IP model, but why even have a model? Alright, so what the beauty of the model is we can, one reason is, as any IT job, you can use this model to help yourself with a problem. So it's a problem solving, right? You can ask yourself physical, which, as we'll find out, that has to do with power. Is it turned on? All right. Is it getting power? Data link. Is there a MAC address going on? Do we have NetBlink on our network interface card? Network. Does it have an IP address? Is it getting an IP address? Does it have a default gateway? Transport. Is it failing? Is this port number blocked by something? And then the session. We're gonna just go to the TCP. The session, presentation. They have to do with graphics, and they're not really part of the troubleshooting. I probably use the TCP/IP. It just goes to the application. Is the application working? Is the application crashing? What's going on? Something like that. But it builds a model where you can shoot from the top to the bottom up, or somewhere in the middle. But we know that the protocols work in this way, and so it helps us troubleshoot things. So it assists in protocol design because protocols that operate at a specific layer have defined information that they act upon, and a defined interface to the layers above and below. Fosters competition because products from vendors can work together. Alright, so that's the difference. This open standards. Is before Novell's building their own thing, everybody's building their own thing. Now everyone's building on the same thing to work together, and so that fosters competition. You have to advance your technology so that people want it. Prevents technology or capability changes in one layer from affecting other layers above and below. We'll explain that more as we start studying it. Provides a common language to describe networking functions and capabilities. Alright, so you guys can look at protocol and reference models, but it's not really important. So the OSI model. A lot of people say it's no longer used, but it's 7 layers: physical, data, network, transport, session, presentation, application. Memorize those. Okay, you're going to memorize what they are and how to do them, but you need to memorize the numbers immediately because you will be tested on these. Then we have the TCP/IP model. So that one was 7. So the TCP/IP model is 4, and on the newer model, it's kind of 5, but it's still 4. And why they did this is the physical is kind of hard to discern when we're talking about straight networking from the data. And so we have the network access, which I also call the data link, which is probably bad because in the OSI, layer 2 is the data link. So I guess this is the network access layer, the internet, which is similar to the network layer, the OSI, the transport, which is the same as the transport in the OSI, and then all of the applications, those top 3, application layer, presentation, and session, are all compiled into one. And so here's our comparison. And as you can see, they're compiled into one, but they're kind of similar. If you look in the book, Odom's book, he has the new OSI model. I don't think it's in here. Alright, so data encapsulation. So we have segmentation, which is how networking works, right? It sends smaller pieces from the source to the destination, breaks it up breaks it into pieces, right? And so we'll just watch the video. Bam, bam. So it could be sent on different sections of the wire. Whereas multiplexing is breaking it up in different timing so that both people can send. Bam, bam. So they're both segmenting data into, they're coming out in different pieces to access, but then they're multiplexed across the wire, which is just a timing, or what does it say up here? Interleaving the pieces as they traverse media. So basically it says, hey, you're going to send on this timing frame, and you're going to send on this timing frame, and that's how they know how to get back. And it's used with fiber optic in different ways, and copper and wireless. All of them have different ways of multiplexing. So now we go to PDU, Protocol Data Units, which each layer of this model has a PDU. Alright, so these are the PDUs right here. So layer 7 PDU is, or not layer 7, because this one is actually looking at basically the TCP IP model. And so it says for the application layer, it's data. For the transport layer, it's a segment. Then the segment's broken up. For the network layer, it's packets. Then frames. And on the wire, how is it sent? Bits. Okay, so the ones and zeros are bits. They create frames, which create packets, and that's what you can see right here, right? That's what it's trying to show you. Is this is the complete frame. So we have a frame header, a frame trailer, a network header, transport header, and then the data. And so then that's sent to a computer, and as it assembles frames, then it breaks it down, goes to the network header, and it says, oh, where do I, as a packet, where do I send it? And then that segment is the data from the transport layer being sent, and so it sends that. So this is actually happening on a network device. The frames are actually what's passing across the wire, and then from this device to this device, they're breaking it into these different, they're passing it down the stack, I guess. But the most important thing on this is to know that your physical layer, this would be a physical layer, bits, data link is a frame, network layer is a packet, transport layer is a segment, and application is a data. You will be tested on that non-stop, so good thing to memorize, as well as the OSI model and the TCP IP model. Okay, so encapsulation. So that's basically what we were talking about. So we'll just run over what is encapsulation. So we want to access the web server. Alright, so that's in the data. So that's inside the data. So we start with that data from the server, and then we put on our TCP port numbers. Alright, so it says HTTP. Then we go to IP, and so we put the destination and source IP addresses. And then we break it down into frames with the Ethernet header, which is going to tell it when to start, where the ones and zeros start, where the frames start, how many frames, where to start and where to stop. Okay, and so from the Ethernet, we have the line, so there's one and zeros. The web client receives it, and it's going to take those ones and zeros and de-encapsulate, which is probably what they're going to show in the next picture, where it actually breaks those ones and zeros back into the data it's received. So here we go. We're going to de-encapsulate. Before, the web server encapsulated the data, and now we're going to de-encapsulate to get the data. So we take off the Ethernet header, take off the IP header, take off the transport header, and now we receive the data. Alright, network addresses and data link addresses. Alright, so network layer is what we call the layer 3. And so the network addresses, I've kind of talked about this before, it's the source IP address and the destination IP address, right? Where it's coming from, the IP address where it's coming from, and the IP address it's going. Such as if I'm going to Google, my destination is 8.8.8, and my source address is 192.168.1.1, or whatever my IP address is. Okay, then we have a data link, the layer 2 addresses, and this is the address that's used by switches. So the network addresses are used by things like PCs and routers, which are layer 3 devices. Switches are layer 2 devices, and so they use the data link address. And so this is also called the MAC address, or the physical address, and so it has a source data link address and a destination data link address. And that's used to send. So we can think of the network address is our, remember we talking about, this is our house address. And then the data link address is the actual name. And so it says, hey, this piece of mail came from Don Cray and it was sent to Santa Claus. I don't know who it was sent to. Okay, so that's what the data link addresses are telling you. Alright, so we're starting with how we communicate from a device. So we have a device of 192.168.1.110, right? And let's see, where is it sending it? It's sending it to the source address of 9, right? So the FTP server. And so we see in the data link, it's going to put this MAC address, which it learned through a thing called ARP, which I think they're going to talk about in a second, or in the next, no, must be in a chapter coming, but this PC has mapped this MAC address to this IP address. So it's going to send anything with the IP address of 9 to CCCCCCC, right? And it's sending it from AAA, right? And so as it sends it across, it makes it there, and then if this FTP server was to send it back, these would all be inversed, including the port numbers that you can't see right now. Anyways, read through that if I didn't explain that well enough. We'll keep hitting that too. So, okay, so here's our ARP, and so what ARP is like I said before, this switch is a layer 2 device, so it only works on MAC addresses. Now this router and these PCs and this web server, they're layer 3 devices, which means they only work on IP addresses. And so we have to have a protocol to map layer 2 addresses to layer 3 so that we can have switches forward on our frames. And what that is ARP. And so ARP maps layer 3 addresses to layer 2 MAC addresses. And so what it's doing is, if I'm going to send it somewhere and I don't have the MAC address, I send an ARP request, and that ARP request comes back and tells me what the MAC address was for that FTP server. Alright, so accessing remote services. Alright, so when we go outside of our network, we need this thing called a default gateway. So inside our network, in our most common network, just a switch, we can send everywhere, right? They're in the same network, and it doesn't need a default gateway. And if you look at your static configuration of your IP address or your dynamic, it has a default gateway because you want to get to the internet, and the internet's not in your same network. So the only time we need a default gateway is when we're getting out of our network. The default gateway is how I get out of my network. That is all it is. And so it has to be in your same network, and I guarantee someone listening to this is going to put their default gateway as something over here, which each router interface breaks down a network, so it has to be inside of this network. So the default gateway is right there because it's the router, and so the router routes to different networks, so it's always going to be a router that is your default gateway, but it has to be in this network as well, right? So probably the default gateway or the next default gateway, well, it's called default route. We're not going to go there, but the default gateway for this network over here is this router, and because that's how this web server gets out of its network, and so that's what a default gateway is. If I'm accessing resources outside of my network, I need a default gateway, and so I'm going to send my traffic, anything that's not in my network, to my default gateway, and it's either going to send it there or it's not, and the traffic's going to fail if it does not have a route to wherever I want to go. Okay, moving data in the network. This is pretty much what I've been talking about, where all this is doing is it's the same thing with the destination and source. What happens as data moves, when we hit layer 3 devices, they rip off this Ethernet header and replace it. So layer 2 addresses are only LAN local. And so what that means is, remember, this is a LAN, and so these devices only use ARP within their network. It's stopped right here, which is, this is a broadcast domain where the broadcast stops, right? This is default gateway, this is where this network lives. That's an entire network. So there's different MAC addresses right here because that's a different network, and right here that's a different network. How do we know that? Because those are routers and they have to be different networks than on each interface. And so this has the MAC addresses are stored here, here. There's a different one for here and here. But as this traverses across, it rips off the source and destination MAC address, looks at the network, and then sends it on its way, which rips it off. So each one of these routers would actually rip this off and change it as it goes along its path. So at first, let me change colors here. At first, we have a destination, or this is the source, and this is the destination. Now the IP address is always of this server. That doesn't change, but the layer 2 changes as we go across. Okay, so that was the first one, and then it changes to right here. This is the source address, and this is the destination. And then it changes to right here, source, destination, and then we're back to this one will be the source, and this will be the destination. So in this tag will be ripped off 3 times as it goes across, right? It starts out here, and then it's ripped off, replaced, 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 and then when it sends across, it's going to do the same thing. But the layer 3 addresses stay the same, except when it comes back, then they'll be inversed. And if you're not understanding what I'm saying, we will talk about this more. So, yeah. And I guess that's chapter 3. Once again, if you have any questions, feel free to post on a discussion or send me an email. Have a nice day or night, or maybe even